It's 3:30. Let's get started. Hi, my name is Layman. Little introduction of myself. I'm a 2015 HSC graduate from Cherry Tech. I've been tutoring for 6-7 years now, mainly in chemistry, high school, year 11, year 12. The purpose of today is to go through the top 5 questions, specifically the reaction pathways for Mod 7. So I shared this yesterday, but we went through identifying organic compounds yesterday with different spectras. Today we're going to work on the second highest marked question, which is the reaction pathways for chemical synthesis. So this one consists of 6.5 on average marks. As you can see, it wasn't in the 2022 paper, but 2021 had 13 marks. So hopefully this one will come up in this year's paper, as I believe this one's quite easy to get marks off if you really know your reactions and know your conditions as well. So let's get on to it. So question 32, if you guys need references of this one, so this one is from Abbottsley Trial 2021, question 32. These references will be at the bottom of every question, so if you guys need to know where it came from, feel free to look at those papers if you've got it. Okay, so the concept of these sort of questions is you've got a reaction and you've got a particular compound that you want to start from, and how do I get to the final product? Now, this is especially important in industry. Not that you guys might need to be concerned about this, but I always like to touch on the why before answering these questions, as it allows us to build a purpose of doing this question as opposed to just doing it for the sake of it. So these questions are built across industrial processes. So you might not know what chloropentane is for, but there's a use for it in industry, which is sort of related to the whole Mod 8, the last section of Mod 8. So doing these questions allow us to identify the types of reactions that occur, the reactants that we need, catalyst, reaction conditions, etc. So let's hopefully get through this in the hour. So question 32, Pent 1 ion is reacted with hydrogen gas and platinum to give us compound A. So this one is a very simple hydrogenation reaction. So I don't know if you guys know the names of the reactions, but here they are for you. So hydrogenation just means I've got a triple bond in this particular case, and I want to break one of those triple bonds to a double bond, and I want to add 2 hydrogens to the subsequent bonds of those. So what does that look like? So draw the compounds of compound A and C and identify the reaction conditions B and D in the boxes below. Compound A. So pentyne is a 5-chain molecule, and it's saying Pent 1 ion. So ion is a triple bond, and after hydrogenation we've got a double bond. So 1 meaning the double bond or triple bond, in this case the triple bond is on the first carbon. After the hydrogenation reaction, the triple bond becomes a double bond. So what we do here is we do C double bond there, and we just fill the rest with hydrogens, and that will be our product. Now, what is the name of this product? We're not explicitly needing to name this product, but for the purposes of naming this product, this one is called Pent 1 ene. So the ene just means double, the ion just means triple bond. Let's write that there for notes purposes. All right, reaction condition B. So from A to pent-2-ol is a hydration reaction. So what does a hydration reaction require? It requires water, but it also requires dilute sulfuric acid. That's a pretty stock standard one. So from penta-2-ol to reaction through reaction D gets us 2-chloropentane. This is a substitution reaction. So the substitution reaction requirement is just adding HCl, which is our hydrochloric acid. Pent-2-ol, cold, dilute, acidified permanganate gives us compound C. So this reaction is known as an oxidation reaction. Simply speaking, an oxidation reaction is a reaction that allows the carbon to bond more to the oxygen. Either that's a C double bond O or an OH. So from a secondary alcohol, we know that secondary alcohol, let's do a revision. For, primary alcohols, they oxidize into aldehydes and then subsequently to carboxylic acids. The secondary alcohols, they oxidize into ketones, and then tertiaries, they don't. No reaction. Oh, very long N. No reactions. So compound C, what is compound C? So compound C is a secondary alcohol, so it's a ketone. So what's the ketone equivalent of pent-2-ol, or of a 5-carbon chain ketone? So that's just C, C double bond, C, 5 carbons, and we add the H's in there. Oh. So one thing that is quite interesting is drawing out the full structure. My hand's going to be really tired by the end of this, but hopefully in your exam you only need to draw a couple of structures, so you don't need to draw all your H bonds, CH bonds, sorry. I have a personal preference of drawing condensed structural formula, which are your CH3, CH2, etc, etc, etc. So just an easier, less lines to wash, to write. Okay, so that's question 32. I thought question 29 from AshCam 2022 trial was very interesting. So they've actually combined a series of different things in Mod 7. And I wanted to highlight this in this particular revision stream just for revision across the whole of Mod 7. I know that this specific one is mainly related to the first reaction, but hopefully a little bit of revision for the subsequent two. So the first, we need to talk about, so what this question is asking. Propane is an important starting material for many products. A student wrote the following notes about propane and its products. So these are the notes. Explain the student's notes, include equations in your answer. Now, I do understand that these amount of lines might not be enough for me to write on here, but hopefully it'll be enough when you do print it out, or if you don't print it out, writing it in, hopefully you'll squeeze it all in. So propane is an important starting material for many products. Explain the student's notes. So let's start by doing the reactions. Okay, reactions, making a subheading or heading helps. So let's break down each of these reactions one by one and say what reactants, what catalysts, what conditions we need. So CH3 to C3H7. Okay, I should have probably left some space for that. So we need to add in a HCl. So gas, probably gas as well, gives us C3H7Cl. So this is the above reaction is an addition reaction to propane. That's really it. That's one. C3H7Cl plus NaOH gives us, now the state's gas, probably aqueous, C3H8O. Now, what is this? This is an alcohol. Now, the question is this a primary alcohol or is it a secondary alcohol? Or secondary alcohol? We can answer that by looking at what this is. Okay, so we know this is an alcohol. An alcohol going into that looks like a ketone. Ketone. So the ketone from a alcohol, that alcohol most likely will be a secondary. Okay, so we can say the above reaction is a substitution reaction. Yep. Reacting NaOH with chloropropane to give us a secondary alcohol. I.e. propan 2-ol. Third reaction, C3H8O, big line, C3H6O. Now, it's an oxidation reaction. What do we need for an oxidation reaction? So oxidation reaction shown above using, now there's two things we can use. We either use acidified, which is denoted by the H+, which we also see there, permanganate, MnO4-, or we can use acidified chromate. So these guys are just very oxygen-rich substances, which pulls away, which provides the oxygen sources required. Using acidified dichromate or acidified permanganate. Beautiful. Okay, so that's all the reactions talked about. We can then look at molar enthalpy of combustion. Molar enthalpy of combustion. Now, if you remember this is just talking about how much heat energy is released for every mole of that particular fuel source. So in this particular case, we're looking at propan-2-ol. It can undergo complete and incomplete combustion. So what is complete? What is incomplete combustion? Complete combustion is when there is a sufficient amount of oxygen in the reaction. So in this particular case, we form two products only. We form our water and we form our carbon dioxide. So those are your stock standard products that you form. Now we need to balance. How do we balance? If you guys don't know how to balance, don't be concerned. Hopefully we still have a bit of time for you to catch on to this. So we look at the hardest thing we can balance first. AKA, we want to balance this guy and probably these guys. So we will leave oxygen till last. So we can either start with our carbons or we can start with our hydrogens. Let's start with our carbons because, I don't know, I like to work left to right. So we've got 3 carbons on the left, 3 carbons on the right. We've got 8 hydrogens on the left, and we also want 8 hydrogens on the left. So we can slap on a 4 there. So as a result, we can then look at our oxygens. We've got 4 oxygens there, and we've got 6 oxygens there. So what we can do is put in a 5 there. And of course, our states. Don't forget our states. And that's it. That's a complete combustion reaction with propan-2-ol. Let's do a... Let's do a continuation of this question. Incomplete combustion, what does that look like? Incomplete combustion is when there's insufficient oxygen in the combustion reaction. What does that look like? What products do you form? There's 2 products that you form in addition. Now, which are your C solid, which is your soot, and then also CO, carbon monoxide. Now typically you can form all of the above, so you can form CO2, you can form CO, you can form water. For the simplicity of typical questions, they should tell you what to form. If they don't, you need to make an assumption about what you form. Whether that's assume formation of. Now, to make your life easier, you can either say just the one, or say you got both, okay? It's going to be hell if you decide to put all of them in there, because it's going to take you a forever amount of time just to balance this. So I'm just going to do one example. I'm just going to say CO. I'm just going to say CO is formed. So what happens? C3H8O liquid plus oxygen gas gives you CO gas and water. Now our CO balancing 3, 4. Now we've got 7 oxygens on the right hand side, so we need 7 over 2. Okay, so as you can see, the difference between, let's grab our pen, difference between the number of oxygens here, 3.5 or 7 on 2, versus here, 5 oxygens, insufficient, right? Pretty straightforward, right? Now, what's that last bit? C3HO has a higher boiling point than C3H6O. So what does that mean? Boiling point. Love those questions. Oh, sorry. We're not done with that question. Sorry. We're not done with that section. We still need to calculate these numbers. Use these numbers. Okay. First thing we can calculate is we can calculate Q. Q is the heat energy. Okay. So we can say 180 grams. Now this is assuming that the density of water is 1 gram per cubic centimeter times 4.18 joules per gram per Kelvin times 42 Kelvin. Now this equation comes from a lovely MCAT. M C delta T. M is the mass of water being heated. Now, a lot of my students always get this confused. This mass is not the mass of the amount of fuel you burn. The mass of fuel you burn is used in a later subsequent equation. C is the specific heat of capacity of water. Heat capacity. And then delta T is just temperature change, right? Now, what does that equal? I don't have my calculator because I gave it to one of my students, but I did work it out previously, and you guys can cross-check that with me. That looks to be, sorry, my computer's a bit slow. 3,16800. Nope, sorry, there's no 8. 3,168. Sorry, why do I keep writing an 8? There's no 8 in there. 3,168.8 joules. Okay, that's our energy. We want to look for delta H, right? What's delta H formula? Negative Q over N. The negative just denotes that it's exothermic. Okay, typically the reaction is burning, releases heat. Okay. Okay, so delta H equals to negative Q being 3,160.8 joules. Now I need to convert the joules to kilojoules. So how do I do that? So I just divide this one by 1,000 joules per kilojoules. Yeah, that's just simply doing a unit swap. So I can just do that. That's 31.6008 kilojoules over. Now my moles, what's our moles? We use 1.05 grams of our propanol. So that's 105 mass over molar mass, 3 times 12.01 plus 8 times 1.008 plus 16. Okay, again, sorry, I don't have my calculator. I did these earlier. And that number equals negative 180.589 024 ... kilojoules per mole. Now, why is this number so important? Because it allows us then to calculate the theoretical one, and then allow us to compare the theoretical with this number that we just calculated. And this one I'm going to denote here as the experimental, EXP, of our delta H. Sorry, should really write that a little bit clearer. Delta H is of our experiment. Okay, now we can work out the delta H of this line, the theoretical one, based on our delta G. Okay, delta G is our Gibbs free energy. If you guys forgot about that, hopefully you guys will look into that. Gibbs free energy tells us the spontaneous nature of our reaction. So as a side note, delta G less than 0 equals spontaneous. Delta G greater than 0 means not spontaneous. We know combustion reactions are spontaneous at above certain temperatures. So we're going to look at here now. So delta H, that's what we want to try find, and that's our theoretical. We know our delta G, which is negative 207.8 kilojoules per mole, minus, here, sorry, on the right hand side again, temperature, which we need to remember to convert to Kelvin, which is 298.15 Kelvin, times our entropy, 193 joules per mole per Kelvin. Now, my students always forget this, and I'm so sorry to keep banging on this, but you really need to convert this unit to kilojoules, all right? This is by far the most common mistake I've seen, is not converting this joules into kilojoules. Okay, so we need to divide this number by 1000. Okay, so therefore the delta H theoretical is 278.5 minus 298.15 times 193 divided by 1000. All right, and that number happens to be 2020.95705 ... kilojoules per mole, and don't forget the negative sign, meaning exothermic. Now, from this we can calculate the percentage efficiency. So, as in the opposite, the 100% would be 100% efficient, meaning there's no heat loss, but you're bound to have a heat loss in most cases. So what we do here is we do this. We do the experimental over the theoretical, which is 1808.589 ... over negative 2020.95705, and as a percentage, which is calculator 98.4917%. And if we were to round this, not that this question is asking, but we want to express as much information as we can, what do? We do how many sig figs? We use two from the 42, so let's do 89% 2 sig fig. Okay, so again, two things to note: always end your answer with a, oh, what's going on there? With a percentage, and also with the number of sig figs that you've used. Sorry, the units and also the number of sig figs you've used. Just to denote to the marker that you haven't overtly increased the accuracy of that number, and also what units are we looking at, okay? Anyone have any questions? Please leave them in the comment section. I will have a look at those and answer those comments that are left there. Doesn't have to be specifically about this topic. It could be anything about HSC chemistry that you guys are having issues with. Okay, so next question. I have lost the question number. Oh, question 27 from Barker, Year 12, Trial 2019, question 27. Yep, perfect. Okay, so compound F may be synthesized as follows. So we've got these flowchart typical that we typically see. Great. We have to draw stuff. Lovely. So how I typically target these is you look at the ones that's already drawn for you. Okay, so this one and this one. You can work on either pathway. Let's work on the left. I'm a kind of left to right person. So what is this? This is ethanol So we've got two pathways. We've got an up and a down pathway. Up, we have to add water to a particular compound, catalyst, to give us ethanol. Okay, that's pretty standard. How do we do that? So if we go the other way, it's minus the water and another catalyst, okay? So this reaction going upwards is a dehydration reaction. Going down, this is a hydration reaction. Now the catalyst, you guys might know this, the catalyst for dehydration is concentrated. I can't write for 1 second. Concentration, concentrated H2SO4, and our hydration catalyst is dilute. Now, this one's a no-brainer. Try to just think about it, use a bit of logic here. If it's concentrated, there's less water, and it wants to take the water in. If it's dilute, there's a lot of water there already, so it can supplement the water to that compound. So, compound A. What is compound A? Lose a OH from one carbon and a H from another carbon. So what I get C double bond H and H, H and H. So this is ethene. Lovely. We've seen that a lot. Now let's work downwards of ethanol. Now this is, I'm sure you guys have seen this already. This is dichromate. Ion acidified. This is an oxidation reaction. Oh. What does that do? It turns that into carboxylic acid. So the carboxylic version of a 2-carbon chain is a ethanoic acid. So this is ethanoic acid. Perfect. We can name this. All right. We can start on the right hand side now. 1-chloropropane. 1-chloropropane. I've added HCl to compound C to give me 1-chloropropane. So 1-chloropropane looks like this. 1-chloro. So it's probably hinting towards another alkene of some sort, okay? And this particular alkene is a propene. So again, you guys know how much I love my structural formulas condensed. Now from my propane, I go to a compound E. Now it looks like there's something that's missing here. It's not showing up here. I don't know why, but that's okay. There's something we add here, and this something, I'll just draw it in another color so we can clearly differentiate it, is, oh, no, not, oh, it's showing up again, not NaOH. Oh, so H2O, just in case it goes again. So what does this give us? H2O, it's a substitution reaction, and what it does is it substitutes the chloro, and it becomes our propane 1-ol. C, 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 OH, H, 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 H. Cool. Propane 1-ol. Propane 1-ol reacts with our ethanoic acid in the influence of concentrated sulfuric acid, gives us what? Now this is an esterification reaction. It's to make an ester. Now, I ask this question to my students a lot. What is the ester bond? Okay, this is the ester bond. So your esters always have this. Okay, just like your other functional groups, this tells us it's an ester. All right. Another example is, what is your amide bond? This is your amide bond. Cool. It's not an amide if it doesn't have this. Cool. So let's continue drawing our structure. All right, so how do we draw this? It's an alcohol plus a carboxylic acid. And we know these guys, they join through the, I'll use another color. Let's use blue. They join through this, there you are. join for this. Oh, okay, never mind. Never mind. They're joined for this bond. So imagine your carboxylic acid and your alcohol are next to each other. Oh, there we go. There we go. There, it's working. They bond through this, and what comes out? Now, esterification is a condensation reaction. Condensation reaction, which means it produces water. The water comes out and you bond through this oxygen. So what that means is anything on the left here is your carboxylic acid, which is your ethanoic acid, which is this. And on to the right of this O is your alcohol, which is 3 C's. I'm going to cheat a little bit and draw my condense. Cool. So this comes from your alcohol, and this comes from your carboxylic acid. Okay, and they lose the OH in the middle. They both lose the OH and they join through the O here. Okay, if I was to cover this side, okay, it's really hard to do that. Let's insert a box. I can do that. Oh no, let's do a shape. Okay, so if I look at it like that, this is just my propanol, right? If I have a H here. If I cover this side, that's just my ethanoic acid if I have a H here, right? So if you ever forget how to do it, draw each of them side by side with a pencil, and then cover both of them, cover one of them, and say, okay, that should be where my alcohol is connecting to. I should rub off the H there. Okay, that should be where my carboxylic acid is connected to. So rub off the H there, and then rub off the one of the O's as well, and then join through a common O, and then this is what you should be left with. Okay, this one is called, we like to call it the alcohol into alkyl, and our carboxylic acid into carboxylate. Yep, carboxylate. So what is that? This would be propyl ethanoate. Okay, that's the name. Again, any questions on this one, just please leave a comment down below. I will answer it, every one of them. Question 27 from Barker 2020. Love the Barker questions. So, the flowchart below illustrates the process involved in the synthesis of some organic compounds. Compound A, B, C, D, E, F, process Y, process Z. Okay, using IUPAC nomenclature, identify each of the compounds listed in the flowchart. 6 marks. Okay, great. A, C3H6. Okay, there's only one compound you can get. That's propene. Now, does propene have a number? We always just number if there's a difference. If the numbers between, if the numbers that, different numbers that we place onto the wording, if they're both creating the same molecule, we can ignore that. We can make the number redundant. So compound A, propene. Not one propene, not two propene, because they're the same. B, let's go down this way, left to right. Dilute sulfuric acid. So this one is a hydration reaction. Dilute, okay? Remember that. Dilute means hydration. Concentrated means dehydration. So we go to compound B, which oxidizes. Now this is an oxidation reaction. Oxidizes to give you propanoic acid. Okay, so this most likely is our primary alcohol. So B is primary alcohol, so propan 1-ol. Now between numbers and letters, we use a dash. If we're using numbers and numbers, we use a comma, okay? Just as a tip. C, So it's an isomer of B. The only isomer of B with propene is, with propan-1-ol is propan-2-ol. Very straightforward, hopefully. D, oxidation of compound B. We know it's a primary alcohol and there's an intermediate product for oxidation, which is your aldehyde. So we know our propan-al is our aldehyde counterpart to a 3-carbon chain aldehyde. Where is E? E is not the propanoic acid. E is the propanoic acid plus the methylamine. Okay, great. Finally see a amidification reaction. So this is an amidification, aka a reaction that creates an amide. So what does an amide look like? I drew it on the other side before, but I think I closed it. So that's your amide. Now your amide could be primary or secondary amide. So primary is this. Primary is this. And not primary, secondary is this. Okay, so we have a secondary amide here. What is that? The naming nomenclature is very similar to an ester, okay? Instead of putting the alcohol, carboxylic acid, we put the amine and then the carboxylic acid. Okay, we still change it to the equivalent alkyl group and the carboxylate. Okay, so what do we change that to? We change that to methyl. But instead of carboxylate, we change that to the amide. So the propan amide. Cool. That makes sense? Hopefully it does. Doesn't? Leave me a comment. I'll explain further. F. Compound F is propanoic acid and ethanol. Process Y. Process Y looks like esterification. Okay? Esterification. Compound F, ester, woohoo, alkyl, carboxylate. Ethanol, so we do ethyl. Propanoic acid, we do propanoate. Cool. Draw full structural formulas for compound E and F. Compound E is our methyl propanamide. So how do we draw this? We do CH. Okay, it's requested for full. Okay, so I can't cheat here. Nitrogen. C double bonded O. C H H C H H H. So 1, 2, 3 for your propanamide, and you've got your methyl propanamide. F is our lovely ester. We love those. C O. I'm going to draw this the other way around to the one I drew on the previous question. Propanamide. Yep. Okay. Draw those hydrogen CH bonds in. Great. Structures. Done. Now, the question then asks, identify processes Y and Z. Y is esterification. And then C is glucose to ethanol. Oh, okay, this is an interesting one. Do you guys remember this one? Fermentation. One of the other ways to produce ethanol. Okay, one way is through biomass to give you fermentation. And then the other way is through petrochemicals, which is your fossil fuels. Okay, this is love those long response questions about assess the impacts of creating ethanol from biomass or from hydrocarbons dug from the ground. Just as a bit of revision as well, fermentation reaction, lovely. Please remember this: C6H12O6 aqueous. Single-headed arrow. C2H5O. Now this is also aqueous. I'll explain later. C2H5O and also CO2. Now balance, that's the balance, and this is gas. Now you only produce about tops 15%, so that's why it's aqueous. If this was 100%, then this would be liquid, but it's not 100%. Okay. Now, there's a couple of experimental conditions for it. Okay, so the first one is it needs to happen in needs to happen in about 35 to 37 degrees Celsius, and you need a catalyst. Okay, this catalyst is yeast. Okay. Now there's no need for like, oh, you need to put it in dark or, you know, specific lights for this to happen. Usually it happens in anaerobic conditions, aka no oxygen. So that's why you typically have it capped off, so that there's no oxygen that can flow in. So, but you know, this asks for two conditions, so we just write those. Esterification, experimental condition. Ah, lovely. Concentrated sulfuric acid. Now I'm gonna answer this question later on, but I'll get you guys to think of it first. Why do we need concentrated sulfuric acid as a catalyst? I'll leave that with you for the moment. I'll answer it hopefully before the end of this session. The other experimental condition is we want to heat with reflux. And I'll explain why we do that. Again, there's another question at the end of this stream just for this particular esterification reaction. Okay, moving on. 34, question 34, 2019 from HSC. Lovely. Hopefully you get something simple like this. The following reaction scheme can be used to synthesize ethyl ethanoate. Outline the reagents and conditions required for each step and how the product of each step could be identified. Okay, great. So the product of each step. Okay, so let's talk about step one. Oops. Step one is CH3CH2Cl. Let's say that's a gas, and it goes to your ethanol. So that is a substitution reaction with NaOH. That gets us CH3CH2OH. The product of this could be identified, ethanol, by, we can oxidize it, which is step two. Okay, could oxidize with permanganate. So it would change from purple to colorless. Okay, that's what you should observe when you oxidize it with permanganate. Step two is ethanol. Oh, I forgot the state of that. Let's say that's also gas. Gas. Oxidation. Now, do you remember our oxidants that we use? There's two. I'm just going to do one. Lovely permanganate. Remember these formulas. They might cost you a mark, maybe. Hopefully not. But if you can write it, remember these oxidants. That would be really helpful. How do you identify CH3COOH? Now, carboxylic acid, there's a very general one that you use. You add NaHCO3, which is our baking soda, if you guys don't know this already, and that will create CO2 gas. Now, for my students who hear this from me a lot, I always say this. I always have this equation. Let's write an equation. NaHCO3 plus CH3COOH gives you CH3OO aqueous plus H2O plus CO2. That balance? That's balance. Perfect. Yes. And how do you detect CO2? Okay, this is another one to remember. Okay, we use the lime water test. The lime water test involves blowing or transferring the carbon dioxide gas into lime water. Lime water is this bad boy here, Ca bracket OH2 bracket, aqueous, and that gives us a cloudy precipitate solution, which is not gas, which is a solid, and you guessed it, water. That's balanced. Yes, that's balanced. Now the presence of the milkiness, okay, milky, cloudy solution is the presence of CO. Cool. Okay, step 3, esterification reaction. Involving ethanol and ethanoic acid in the presence of H2SO4, concentrated, reflux with heat. How the product of each step could be identified. How do you identify an ester? It's usually got an odor to it. You can run it through IR, HNMR, CNMR, and cross-reference spectrums. Cool. Sure, we should have time. Question 31. Compound G may be synthesized as follows. Compound A reacts with dilute sulfuric acid, which is process X, to give you butane 1-ol, and compound C. Okay, let's start with that. We have hydration, lovely. Hydration. There. Butane 1-ol. Opposite is dehydration, so dehydration of butane 1-ol is our butene, but butene. So let's draw out our butanol. Now, if we have our but1 in there, the double bond needs to happen here, next to it. Okay, so what we're going to get is we're going to get but1 in. Is there but2 in? Yes, there is but2 in, but we're not going to get it here. Reason is because we'll never get the but1 in, but1-ol. Okay, so it's but1 in. C. Compound C is an isomer of but1-ol, which is the other product of your hydration reaction with compound A. So the other compound you're going to get is when your OH is here. So what's that? That's but and 2-ol. Our compound E is a oxidation reaction of our butanol, which is a primary alcohol. Primary alcohol oxidation will give us carboxylic acid. Which carboxylic acid that is? That will be butanoic acid. B, C3H6 again. There's only one formula that you can have with that, which is propene. So propene. D is a addition reaction, actually. This is an addition reaction. Haven't seen those much. Addition reaction to give you D. That is an isomer of this guy here. So if this is 1 bromine, this will be 2 bromine. 2 bromo propane. F is a substitution reaction. How good? We've got one of everything. Love these questions where they just give you all the different types of reactions here. So it's a substitution of this halogen there. So what we get is the substitution of your OH. So what you get is our butane 1-ol. All right, draw the structural formula for compound G from the flowchart. Where's G? G is this one. Process Z is an esterification reaction. Cool. So compound E is butanoic acid. F is, oh, sorry, not butanol. Sorry. Thinking of the other question, propanol. So we've got propanol and butanoic acid. Draw the structural formula of compound G. So that will be, I'm just going to name it first, propyl butanoate. So what would that look like? C, C, O, C double bonded O, C, C, C. So this here is our butanoic acid. This here is our propanol. Cool. So we got there. All right. So C, identify the types of reactions which occur from each of the following. Process X, compound A is converted to butanol. So hydration. Perfect. Hydration. Process Y, butanol is converted to compound E. Process Y is oxidation. Perfect. It's great we wrote those, so we can just fill in the blanks there. Okay, now this is where I would like to explain why we use concentrated sulfuric acid. Okay, now what is our reaction here? Okay, I'm just going to write a very general equation. Okay, alcohol, carboxylic acid, and we have an equilibrium with our ester, and we form water. Now we use concentrated sulfuric acid because, think mod 5, guys. If we have water here, okay, we have water, how do we shift? Now this water, I'm just going to leave the state because we know that water liquid is not part of the equilibrium. But imagine this wasn't liquid water, this is gaseous water. I'm going to leave this blank. The concentrated sulfuric acid is a dehydrating agent, right? We know that from our other reactions where we have to dehydrate our alcohols to give us our alkene. What this does, the sulfuric acid pulls the H2O towards them, shifting the equilibrium to the right. What does this do? This yields more ester, which is what we want. So the purpose of sulfuric acid is to dehydrate the water, pull the equilibrium to the right as a result of Le Chatelier's principle. I'm not going to go into I'm not going to go into explaining what Le Chatelier's principle is, but hopefully on Wednesday, 23rd of October, that's that particular section on it. So you'll understand, or you'll be able to revise for Le Chatelier's principle then. Okay. Now explain why this equipment was chosen to carry out process C. So process C is esterification. This setup. Okay, what do we have here? This is a condenser. What does this do? Condenses the vapors. Okay. What do we have here? We've got a water bath, and it looks like there's a heating plate here, which is very good. Okay, let's talk about top to bottom. Condenser. This condenser we typically call reflux. So we heat this reaction. So the heat comes into this reaction to speed up the reaction. All right, but reaction, our alcohol, our carboxylic acid, our esters, they're volatile, right? They've got low boiling points because they're hydrocarbons. So they're gonna vaporize. They're gonna volatilize. So what do we need to do in order to keep this reaction happening, to keep this equilibrium occurring, is we need a reflux. We need to apply a condenser unit, which will condense, and then in this case it's liquefy any volatile vapors. This prevents the escape of any volatiles, i.e. reactants and products, it's also not only is it a reaction aspect, it's also a safety aspect, right? you've got these alcohols, you've got these acids boiling, you get into your eyes. You're not going to be very happy by the end of the day. Now, reflux is one aspect of this. I would like to comment on the water bath aspect as well. Now, the water bath aspect. So this is applying indirect heat to the reaction vessel. And what does this do? It allows for sorry, I would like to retract the word allow, which prevents the fire hazard of any flammable gases. Okay, now alcohols, they burn. You hate to have a Bunsen burner and having these potential alcohols heating directly and potentially have it drip to the side of the flask and then you burning it up. Okay, so the purpose of reflux is to do two things. Okay, purpose of reflux is to do two things. It's to prevent any escape of the volatiles, which will slow down your reaction, but also safety aspect of having these reactants products into the atmosphere, okay, around you. All right, so this concludes this revision lesson for today. As I said, this is approximately averaging 6.5 marks of your HSC. I'm expecting this to be a very interesting question this year, hopefully, and I hope the best for you guys studying for, I know, bios tomorrow. So if you guys are doing bio, good luck to that. I'll be again here tomorrow at 9 p.m. doing titrations. Hopefully that'll be another interesting stream. And for those who have questions about this particular topic, anything HSC chemistry related, please let me know in the comments below. All right, thanks very much guys, and you have a lovely day.